All right, so a differential equation is just going to be an equation that has some kind of derivative expression. And it can have a first order derivative or it can have a second order derivative, either one. So most of the time, differential equations are written dy over dx for first order, but you can have y prime also. All right, and then the second order, you're going to have d squared y over dx squared. Or you could have y double prime. All right, so differential equations sometimes contain the original function. Or sometimes they're just written in terms of the independent variable. And I'll show you both ways today. Okay, now this is the part that's a lot like what we did in pre-calculus. Sometimes we're going to write our differential equation. In pre-calculus, most of the time it wasn't written like in terms of dy over dx. Obviously, we didn't do that in pre-calculus, but the k stuff is the same. So if a rate is proportional, sometimes it will say proportional, sometimes it will say directly proportional. They mean the same thing to a quantity. Then we would say that dy over dx is equal to k times y. So direct proportion, we're going to multiply the variable by the k. Do you guys remember what we do when it's inverse proportional? Inverse? You divide k by it. So we still have the k, the constant of proportionality. But for inversely proportional, you divide by that y. They all have the k. They all have the constant of proportionality. Okay, so we're going to do several of these problems where we are writing the model. We're writing the differential equation using the words in the problem. K over y for inverse proportionality. Or inverse proportional. All right, so for number one, the number of fruit flies increases at a rate proportional to its current population, which we're going to call F. Write a differential equation to represent this situation, and then we're going to decide if K should be positive or negative. So we want to write the rate that F changes. So that's going to be dF over dt. All right, and we always have the k, so we always have it equals k. And then we just have to decide if we're going to multiply k by something, or if we're going to divide k by something. So we're going to multiply on this one, or what are we going to multiply it by? F. The current population of the fruit flies. What C? No. We don't have a C. This is a differential equation. We will have C's again, don't worry. Very soon, but not today. All right, should K be positive or negative for this problem? Why positive? Because it increases, right? So K should be positive. All right, let's look at number 2. A scientist is studying the relationship of two quantities, S and T, in an experiment. The scientist finds that under certain conditions, the quantity of S increases or as the quantity of S increases, the quantity of T decreases. After taking measurements, the scientist determines that the rate of change of the quantity of S with respect to the quantity of T present is inversely proportional to the natural logarithm of the quantity of T. It's a lot of words. All right, we're going to write a differential equation that describes this relationship. So we are writing an equation to represent the rate of change of the quantity of S with respect to the quantity of T. So I want you guys to write that using calculus symbols. Write what that means. All right, so what do y'all think? Rate of change. Thank you. ds over dt. Now this t is not time, so we're going to use a capital T like they use in the problem. This t is the amount of the quantity t present. Okay, this has to equal k. All right, so it is inversely proportional to the natural logarithm of the quantity of t. So what are we going to do to k? We're going to divide by the natural log of t. That's what it says in the words. All right, yeah, okay? Okay, number 3 is one, like if you're rushing, that you might make a mistake. So 3 says a jogger runs along a straight track. The jogger's position is given by the function s of t, which we almost always use for position, where t is measured in minutes since the start of the run. During the first minute of the run, the jogger's acceleration is proportional to the square root of the time since the start of the run. We're going to write a differential equation that represents this, or that could describe this relationship. What is the relationship between the position function and the acceleration function? No, before, like what we learned a long time ago about position, velocity, acceleration. So acceleration and position? Second derivative, good. So when we write this differential equation, this is one where we're actually going to use a second order derivative. So we would say d2s over dts equals k. All right, so now we have to go back to the words. The jogger's acceleration is proportional to the square root of the time. So what do? Multiply by the square root of t. Good job. All right, let's keep going. You good?
Oh, what?
Okay.
Yeah.
All right, let's look at number 4. The weight of a baby bird at birth, which is when t is 0, is 20 grams. If b of t is the weight of the bird in grams and t days after it is first weighed, then db over dt is 1/5 of 100 minus b, or 1/5 times the quantity 100 minus b. All right, so we want to find the rate at which the bird's weight is changing when the bird weighs 30 grams. What are we going to do with that 30 grams? We're going to plug it in for B, right? We're looking for a rate. This equation gives you a rate, so all we have to do is take our function dB over dt and plug it in. So I wrote a little too big. So that's going to be 1/5 times 70, or 14. And what should my units be for this rate? What do y'all think? grams per day. Good job. All right, so you guys do the second part. Find the rate at which the bird's weight is changing when the bird weighs 90 grams, please. What do y'all think? 2 grams per day. So what happens as the bird gets bigger? Right. The bird grows slower as it gets bigger. Everything that I know grows like that. So the closer you get to the final weight you're going to be, the slower you're growing per day. So what we can say about the rate of change of the bird's weight as it gets closer to the adult weight is just like Joshua said, the rate of change decreases. So the bird actually is growing fastest at the very beginning of its life and then slows down. So what's wrong with this graph? Starts off slow and then increases really fast and then levels off. So that's the problem. It should be more like that. So we would say the rate of change or the slope should be fastest or steepest if you're talking about slope when B is 20 at the very beginning. So the function is increasing because the bird just keeps gaining weight until it reaches the adult size. But the slope is decreasing, which makes it concave down. Okay, and the last example, we have a differential equation. So this is a differential equation that uses the original function and the second derivative. So you'll see a lot of these different types. So we have several choices for y. We're going to decide which ones of these that if we take the second derivative, add the original function to it, that we end up with 0. Okay? So we have to find a bunch of derivatives. So what do you guys think about the first derivative of e to the x? It is e to the x. What about the second derivative of e to the x? It's also e to the x. If I add those together, am I going to get 0? No. So A is a no-go. What's different about B? Or what extra do we have to do on B? We have to do the chain rule, right? All right, so for our first derivative, we have to multiply by the derivative of negative x. What is that? -1. All right, and then we do that again for the second derivative. So multiply by -1. Okay, so again, if I take my second derivative and I add the original to it, I do not get 0. All right, let's look at C. So the first derivative of sine of x is going to be cosine of x. What do you guys think about the second derivative? Negative sine of x. Yeah, so if I take my second derivative, add the original to it, I do get 0. All right, you guys try a D on your own, please. Did you guys get that it works? Good, me too. All right, on E, we're going to do the chain rule again. So, because I have a function inside of a function, so we have to multiply by the derivative of 3x. What is that going to be? 3. So the derivative of sine of 3x is going to be 3 cosine of 3x. All right, what do y'all think about the second derivative? Negative 9 sine of 3x, good. So if I took second derivative original, am I going to get 0? No. All right, you guys try F, please. That one works. All right, so what questions do you guys have?
Wait, how did that equal 0?
Because you have negative 3 cosine plus 3 cosine. We're doing the second derivative plus the original. And they do have them where it is second derivative plus first, so you have to just kind of pay attention to what it is problem to problem. Okay.